Okay, welcome to the today's class. Today we are going to look at the modeling of combinational circuits. We have seen the fundamentals of what do you mean by a combinational circuit and how can we design that combinational circuits we have seen. Okay, today we are going to see how to model this combinational circuits, right? Let me keep heading modeling of circuits. Okay, so the question comes here is why we need to model the circuits. Okay, so as let us look at one of the digital circuit, for example, uh, a digital circuit. Question is why we need to model. Okay. As we have seen in the last class, just a brief idea I have given. Okay, what we need to do. First of all, if you want to verify the functionality of any digital circuits that you have designed, okay, and first you have to go to the lab and whatever the design that you have done, you have to put it everything on a breadboard and apply the inputs and verify the output. Okay, so this can be done. It is very helpful and very easy. We can do it for the small circuits. Okay, for example, the circuit consisting of two inputs and two outputs, for example. Okay, for example, three input and four outputs. Somehow we can manage if the number of inputs and number of outputs are less. Designing the circuit and testing the circuit is very easy in our laboratory. Okay, but as the number of inputs of a digital system is increases more and more, then developing the equations and getting the hardware is a very, very tedious job. Not only that tedious job, but testing is also complicated, right? Because we have to go to the lab. Okay, the circuit consisting of, for example, 20, 30 components that are there. If you want to connect one component to another component, a lot of complexity will be involved in it, right? So that is not actually advisable one if you want to verify your design in the laboratory. Okay, practically it's not possible. Okay, not only design is not only the problem, but also verification is also a problematic thing, right? Okay, so what is the problem here? The basic conventional approach are manual design and verification is not efficient way. It is not efficient way, right? That's the reason why we have to go and model the digital circuits. If this point is clear. So as the complexity of the circuit is increases, design and verification is both are very, very tedious job. Okay. So therefore, what people have suggested that, okay, you model that hardware, okay, and then dump that model into the existing the PLDs, and then you can verify it whether the design is correct or not. Okay. So therefore, what is our solution here is that modeling is basically modeling of circuits is an efficient way to design and verification. Okay. So the question comes here is that what do you mean by modeling of a digital circuit, right? So modeling means that identifying the functionality of this one by means of something. Okay. For example, I can model my digital circuit by using some mathematical equations, right? I can understand something, some logic function by using some architecture that is available, or interconnection of the gates, for example. Okay, there are the different ways to understand about the hardware, and based on that hardware, we are going to use some medium to represent that hardware. Okay, normally this digital circuit is a hardware. It's nothing but a hardware, right? Okay, because the components are available at the instant of the time. Each and every component in a particular circuit will be active. Okay, that means they will work. Okay, so therefore definitely, so the concurrent program, concurrent execution will be happening in the hardware or in a circuit. Okay, so that's the reason why. So the digital circuit is normally people will call it as an hardware. If you want to design this hardware, okay, we are going to use one approach that is called, for hardware, to model, we use one important technique called by using the CAD tools. By using the CAD tools, we are able to model the circuit. Okay, that means the CAD tools is nothing but computer-aided design tools. Okay, these tools are help us to model the hardware. Okay, now what are the CAD tools that are helpful for us to model this hardware? Okay, normally we use Xilinx is a software. Xilinx is the one software. By using the Xilinx, we are able to model our hardware. Okay, so this software will help us to write something about the hardware. What do you mean by a modeling? We are describing something by using some medium. Okay, so what is the medium that is the help us to understand about the hardware? We are going to use some HDL programs, HDL languages, hardware description languages we can use. Hardware description languages. We have a hardware description language that are there. That language is supported by the software. By using that language, we are able to model or describe the hardware. Okay, so the question comes here is that what is the HDLs are available to describe your hardware? That's the question. Okay, we have different HDL languages that are there. By using this one, we are able to model the hardware. So what is that one actually? Verilog is one important language is available, or you have a VHDL language is available, or system Verilog is available. Okay, so therefore by using this one of this language, we are able to describe the hardware. Describing the hardware is nothing but modeling in hardware. As simple as that. Okay, what do you mean by describing of this classroom? What does it mean? If you ask you to describe this classroom, how you can describe? That means how many entry points that are there. Okay, how many number of tables that are there, how many number of lights that are there, which location the lights are there, which location fans are there, which location the boards that are available. All these things come under the description of this classroom. Is this point is clear? Okay, description is nothing but just telling that what information that is there in this classroom. As simple as that. Okay. So therefore, these languages are help us to describe the hardware. That means how the circuit is, what are the different components that are there, how these components are connected from one component to another component. Okay. Where is the input pins are there? Where is the output pins that are there? Where are the power lines that are there? All these things come under the description of hardware. Okay. As I told you that hardware is nothing but a digital circuit, a simple digital circuit. Okay. So therefore, by using this hardware HDL program, HDL language, we are able to describe the hardware, right? So in our syllabus, we are going to talk about the Verilog HDL programming or HDL language we are going to talk about. Once you know one language, then it is the same things will be there in the other language also. Just only minor changes will be there in this one. If you are strong in one language, other language is very simple to understand. Okay, the main purpose is to describe the hardware, nothing else here. Okay, fine. Once we are able to describe the hardware by using the HDL or Verilog, especially Verilog we are using. What is the advantage of using that one? You have described somehow by using some language constructs. Okay, and what is the advantage of doing that? As I told you that instead of designing everything from the scratch, okay, you can write some piece of line of code, okay, then it will design the hardware. That's fine. Now the question is that how do we verify that functionality? How we can verify the functionality? What we can do, so we have a provision that the PLDs that are available, the PLDs are nothing but programmable logic devices. What do you mean by programmable logic devices? PLDs, programmable logic devices. What are those? PAL, PLA, all these things will come under the PLDs, right? What is the advantage of using the PLDs actually? Reusable. It is nothing but reusable. We can reuse the hardware according to your convenience. For example, if I ask you to design the half adder, for example, okay, then you take one exclusive OR gate, one AND gate, then you can do this one. Okay, and that is that particular breadboard is dedicated for performing the half addition, half adder. Am I right? But if I ask the same breadboard is used for the full adder also, then what you have to do? You have to remove all the components and put the full adder related components and make the necessary connection. Am I right? Then I ask you to, okay, please design the 2x4 decoder, for example. Then what you have to do? You remove everything and put the decoder related components there. Okay. What if, for example, the hardware is something like this, the breadboard is something like this. Okay. Some part of the breadboard is responsible for addition. Some part of this breadboard is responsible for decoder. Some part of the component is responsible something like this. That means a big breadboard putting necessary all the components. When I ask something, okay, make the connection on a particular piece of the place where these components are available. You go there and make the connection and put something else, right? If I ask you to, for example, this is a hop adder, this is a decoder, this is a full adder, this is, for example, flip-flop, as for example, a counter. If I ask you to design a counter, means the counter is already available there, just you make the connection, The necessary components are available. Okay, counter necessary components are available. Just make the connection. That means you give the clock signal, where the clock signal you give, where the input signal you give, where the output that you will get in. Just that kind of configuration is enough. Am I right? Okay, so this kind of approach, the people are called PLDs, programmable logic devices. That means all the resources are available at one place, okay, and make the necessary connections on a required components. Is this point is clear? That is all about PLDs. Okay, so as the complexity of the circuit is increases more and more, these PLDs are also not up to the mark. What is PLDs are, especially we talk about PLA, programmable logic arrays, PALs, that we can call it as. Okay, as the complexity increases, we go for the CPLDs, complex programmable logic devices are available. We talk about these PLDs in our the class in the chapter number 4 or 5 will come. We'll talk about more on this. Okay. Okay. So, for example, if the complexity is more and more, for example, then people have invented FPGAs. Okay. People have invented FPGAs. Okay. Field programmable gate arrays. The idea is the same. That means provide the necessary components in a particular place and make the necessary connections according to your requirement. Is this point is clear, everyone? Okay. Therefore, the fields that are FPGAs that are available. Okay. Once you model your circuit, once you model your hardware, just dump that hardware, dump that information into this FPGA. That means it is a readily available chip. What is this? It is readily available chip. Okay. So that means it has got n number of inputs, n number of outputs. This is a chip actually. Okay. In this FPGA chip, we are going to dump our model into this FPGA so that this FPGA acts as a decoder, encoder. Okay. Multiple applications that are there. The multiple applications can be implemented on FPGA. Okay. So that is what the advantage of modeling your hardware. Okay. Once FPGA is a real hardware actually. It is a real hardware. Okay. Therefore, they apply the input signals and get the output. And if it is correct, then your hardware is working. Your design is correct according to your requirement, according to your specification. Is this point is clear? Okay. Why we need to model the digital hardware? For the testing, for the design purpose, as well as verification purpose, very easy. Okay. So therefore, modeling is an essential way to design and verify the hardware. Okay. Yes. The question is that, okay, we know why we need to use the model when compared to the manual approach. Then the question is how you can model the hardware. Okay. Now the question is, how can you model the hardware? As I mentioned, that what is the answer for this question? Use the Verilog HDL program. Okay, you can use Verilog HDL. With the help of Verilog HDL, Verilog hardware description language, we are able to model the hardware. Okay, but whenever you're using the language, we have to follow some constructs, right? So whenever you're talking about English language, we need to follow some constructs, right? That is a grammar we have to follow. So many things that are there, right? You need to know what is the alphabets that you're using, okay? And how the sentence will be formed, how the word will be formed, okay? In order to get the meaningful sentence, what kind of grammar that we have to use. A lot of things will be there in this one. Similarly, here also, whenever you would like to write something by using the Verilog HDL, we have to follow the rules that are framed by this language. Okay. So what are the rules that we have to follow in order to realize this one, or in order to describe the hardware? For example, you want to design half adder. You want to model an half adder. Okay. Now look at this one. This is the half adder. We have how many inputs are there for the half adder? 2 inputs, right? Okay. A is one input, B is one input. How many outputs? Two outputs, right? Sum and C. Let me write it. This is a sum and carry. Okay. This is called full adder. Okay. Sorry. This is in a half adder. Okay. Now, if you want to describe this half adder, okay, by using the Verilog HDL, what is the first thing that should come into our mind? What the Verilog says? What you can see for this diagram? What you can see, what you see about this diagram? Input and output information, right? First of all, you have to write what is the external view of your hardware? What is the external view of your design or digital system? What is the external view here? The first thing you should notice that what is the external view? So external view means what? What information should be there? It's simply a name of the block. Okay, name of the block will be there, and input information and output information. That is only we can see about this external view. Nothing else. This one. Okay, inside of this one, we don't know anything. Just like a black box they have given. Okay. So if you want to write a program for this, what we have to, how we have start this particular black box, we normally call it as a module with respect to Verilog HDL, right? Okay. So therefore it start with the module. It is a lowercase letters we have to use. Okay. All are lowercase letters. Why it is called a lowercase letter? So therefore, Verilog, whoever invented this particular programming language, they said that you have to use some keywords. That keywords must be in the lowercase letters. Okay, that's the reason why a black box can be called as a module. Okay, so now what is this name of this module? For example, HA is a half adder. I have written something like this. So this is called the name of the module, but this name of the module we also call it as identifier. What we can call it as identifier. Okay, so but the ID, this is the name of this module is nothing but identifier. But there is some precaution we have to follow when we are writing the identifier. Okay, can anyone tell me, is any question, anything that you learn about identifier? What is the precaution we have to follow when we are using the identifier? Start with, okay, you should not start with number. You should not start with number. The precaution means that negative word that you have to say. Okay, you should not start with number. You have to, it should start with alphabets. Okay, right? So that's the reason why it can be a capital letter or lowercase letter. It doesn't matter. Whatever you feel comfortable to write something about this name, you can write there. Okay, I feel comfortable writing the HA. That's enough. Okay. Next, we have to write what are the variables you're using. What are the variables you're using here? A you're using, B you're using, sum you are using, and carry you are using. Okay, and we have to end this one, this statement by using semicolon. Very, very important. We have to use the semicolon. Okay, this is the first line that you have to write for any programming, for any design. What is the name of the module? What variables that you're using? But it's also important that, as I mentioned, that it's an external view, right? You're using some variables, but you should mention that what is that variable used for? You're using for input purpose or output purpose, you have to mention, right? So you have to write here is input. Input purpose I'm using A and B. Look at this one, I'm using the different colors. The moment I'm using the purple, it means that it is a keyword, just for the sake of identification. Okay. You cannot use these keywords as identifiers. Okay, they have their own meaning, and we should not use for the general purpose, right? What about output? Output purpose, what you have used? Sum and carry. Okay, and then I have to end this module. I'm using this end module. This is the external view of your hardware description. Is this point is clear? There should not be any kind of space between end and module, and there should not be any kind of semicolon, right? If I say something, for example, if I say something like this, okay, instead of this small a, if I write capital A, okay, what will happen? What kind of error it will show you? A is not declared. Okay, so why it is so? Verilog is actually a case-sensitive programming language. It is a case-sensitive programming language. That means if whatever the variable you're using small a, you have to throughout the program you have to use the small a only. If you are using the small a, okay. So therefore, Verilog is actually a case-sensitive, right? Okay, that's the reason why we are not writing in this way. For example, small a we have to write in this way. For example, I'm writing in this way, capital A. Where the modification is required, in the top place we have to use it, or input place that I have to use at the input place, right? Hopefully you catch this point, right? Okay. So now this is what the external view of any digital system, right? You take a decoder, encoder, multiplexer, magnitude comparator, whatever we have seen so far. This is the first thing that you have to do. Okay. But now the question is that what is the internal circuit of this one? That's the question. Okay. So how do we understand about the half adder? How can we understand the half adder? The second point to note is that internal view. Internal view. Okay. So internal view we have to write it within the program. Okay. So what are the different ways to understand about the half adder? That's the question. Okay, by looking at this one, you can say I can easily understand this in half adder. What are the different possibilities to say half adder? For example, if I give the truth table, for example, okay, if I give the truth table is something like this, okay, A, B, sum, and carry I have given in this way, 0, 0, 0, 1, 1, 0, 1, 1. Okay, 0, 1, 1, 0, 0, 0, 0, 1. Okay, I have given the truth table in this way. Are you able to tell that what is this logic, what is the what is this functionality it is? As we have a digital designers, then we clearly understand by looking at that one, it is simply a half adder, sir. You can tell me like this, right? By looking at the truth table, you can see what is inside of it. What is the logical functionality of the half? What is the logical functionality of the digital circuit, right? Is there any other alternative? Is there any other alternative? Huh? If you know, for example, in equation, just I have given equation, sum is equal to A XOR B I have given, and carry is equal to A and B I have given. By looking at this one also, you can say, right? If I give the direct equation, what is the logic function that hardware will do? If I ask you something like this, you can immediately say this in a half adder. You can say like this, right? Okay. What is another alternative way? Any other alternative way? Circuit diagram. If I give, for example, circuit diagram is something like this, you can say also, okay, some exclusive OR gate is I have given, okay, one AND gate is given, okay. I am writing the sum here. Forget about whether the names I have given correctly or not, doesn't matter, okay. This hardware I have given, having two inputs A, B, two outputs, something like this. I have given this hardware, like in a gate examination or somewhere else examination, they will give you this hardware. What is this functionality? Then you can immediately say that it's in half adder simply. They will write half adder, full adder, something else they will write. You apply the input A and B, some 0, 0, and so you'll calculate what is the S and sum. And according to that one, you can say it's in a half adder, right? These are the different ways that are there to identify the internal structure of your hardware. Am I right? Okay, right. So based on this internal view of this any digital hardware, we are going to say that we have a different modeling styles that are there in Verilog. We have a different modeling styles that are there in Verilog. Okay. So, for example, if you're using this hardware and if you want to describe the circuit, what we can call it is, this simply people will call it as gate level modeling. What we can call it as gate level modeling. Okay. For example, if you're using this mathematical equation and describing your hardware, for example, the Verilog has a provision to use any one of this internal structure and you can write the program. Okay. Then this is called, what we can call it as, I think you have done so many labs that you have done, I guess. It's a simply data flow modeling. Then what is the question in it? Data flow model. Okay. Data flow model. Okay. Now, if you're using the input output behavior in this way, just if this is the input, this should be the output. That's it. It is a as simple as a behavioral model, right? Behavioral model. Okay. So let us write the data flow model. Which one is the first thing and which one is the last thing that you can notice? Whenever you design something, where you can start? You can start the truth table. From the truth table, you can develop the mathematical equation. From the mathematical equation, the circuit. That's what we have seen. Not that first equations we develop and then truth table we develop. We don't do that one. And not that we have hardware and from that hardware equations develop. From that hardware I can develop. Not like that, right? Usually from truth table equations, from equations to this one is okay. But let me write for the simple case that I'm going to start with the data flow model. Okay, but anyway, I'm not going to go for this one. Just I'm going to write it in the behavioral model first. Input output behavior only I want to write. Can someone suggest me how to start this behavioral model? How can we start a behavioral model? Assign. Output? Yeah, output is declared as register. Very good. Next. We have to use the always statement, right? The moment if you are using the always statement, your description, it is called a behavioral model. Okay. So therefore, so first of all, what equation, what statement I have to write? Always. This is called always block. Always. Something has to happen, right? So always something has to happen. This is called always block. What we call it as always block. Okay. Always the statements existed between the begin and end must be executed. On what basis the begin and block will be executed? That means we have to write the information about the output within the begin and end block. We have to define the output information between the begin and end block. But when this output will be evaluated, when there is a change in the input, right? Unless otherwise, if they're not changing the input, and what is the time waste process that we are calculating the output, right? Okay. Therefore, we have to write whenever there is a change, at the rate stands for the change in something, then it has to go and execute begin and end, right? So whenever there is a change in A, okay, maybe A can change from 0 to 1 or 1 to 0, that change will enter into this block, or otherwise B change. B can go change 0 to 1 or 1 to 0, it doesn't matter, the change of the B, or A and B simultaneously changing. A is 0 to 1 or B is 1 to 0, for example, or A 0 to 1, 1 to 0, some 0 to 1 also, for example, something like this. So if there is a change in A and B, then go to the begin and block and execute the statements. Okay, so this is called sensitivity list. What we can call it as sensitivity list. Okay, right. So now, what are the changes of A and B is observed? Okay, you said that 0 to 1 or 1 to 0, some changes that you are expecting, but what changes that we have to write within this one? Because of the change, this should be the output you have to mention. Okay, now tell me what you have to write. What change that you're expecting first? What is the change? Okay, look at this one. This is the one, for example, what is the change that you can write? So this is the change, for example. If this A is changing, for B is changing, so it doesn't matter. For example, let me write it in this way. If A equal to 1 bit of 0, okay, this is the binary representation in Verilog, number representation in Verilog. Okay, so 1 stands for number of digits, B stands for number system, B stands for number system. That too, here I have used binary. B stands for binary number, 0 stands for the value. Whatever the digit is there, the digit value I have mentioned here. Okay, if this is the one case, if A equal to 0, that means this is what I'm talking about. And not only that one, B equal to 1 bit of 0. If this is the case, A0 and B0, this is how we have to write. If A0 and B0, then what has to happen? Sum is assigned with, what has to happen? Sum is assigned with 0, carry is assigned with 0. Okay, just I can write some information here. Therefore, let me write here is the sum equal to 1 bit of 0 and carry equal to 1 bit of 0. That's what as simple as that. Okay, just what is the input, what should be the output. Okay, since this is simply a condition, after the if condition, we are writing the two statements here. In Verilog, we should not uh, isolate the sum and carry differently. I want to use this for this condition. These two statements must be executed. Okay, that means we have to write begin and end. We have to write begin and end. Okay, if the statement, if the condition is true, it will enter into the begin and block and it will execute the two statements. Okay, suppose if you're not writing the begin and end, for example, if you're not writing this one, what will happen? Begin and end you are not writing, then what will happen? If A is equal to 0, B is equal to 0, sum is equal to 1 bit of 0 only executed, but carry out is equal to 1 bit of 0 is not at all executed, right? But that condition requires the two outputs. Okay, this is called, this statement is called procedural statement. What we can call it as procedural statements. Okay, If I ask you one question, what are the statements we have to use in behavioral modeling? If I ask you this question, answer should be procedural statements, right? If statement, case statement, for loop, okay, while statement, okay, all these things come under the procedural statements. Okay, right. So like this, only one combination I have written. How many combinations I have to write again? How many combinations I need to write? Another 3 combinations I need to write, right? Okay. It is really how many combinations I need to mention? If I ask you one question, a Verilog is which valued system? Verilog is which valued system? Verilog is actually a 4-valued logic system. Okay, Verilog is a 4-valued logic system. That means if you take any variable, it can take 0 value, it can take logic 1 value, it can take unknown value, it can take high impedance state. Okay, so what are the things? 0 value is a 4-valued logic system. Verilog is a 4-valued logic system or number system, it will follow. That means 0 will consider one value, 1 is one value, unknown is one value, Z is another value. Okay, Z. So X is nothing but unknown. That means whether it is 0 or 1, we don't know. But Z stands for high impedance state. Okay, that means that value is a high resistance path, that is actually. Okay, but here the X means either logic 1 or known values that are there. But the Z stands for high impedance state, high resistance path, that is we can consider. Okay, right. So accordingly, if you take the 2 variables here, how many combinations we have to expect? Huh? If I'm taking the 2 variables, okay, it is a 4-valued logic system, then how many possible combinations I should have? Huh? 2 power n. I told you at the beginning of the class, right? It's a 4 power 2. What is the base system here? 4-valued logic means that 4 base system is 4. 4 power, how many variables that are there? 2 variable. 4 power 2. That is 16 possible combinations. What are the 16 possible combinations? 0, 0, 0, 1, 0x, 0z. 1, 0, 1, 1, 1x, 1z. x0, x1, xx, xz. z0, z1, z, something like this we have to create, right? But our requirement is only 4 is enough for this case, right? That's the reason why I'm writing only the 4 cases. Okay, but here you look at this one. So we cannot write if statement something like this. Instead, if this condition is false, then you go and check this condition. Else if we have tried. If the first condition is not true, then go and verify the second condition. If it is second condition is not true, then go and check for the third condition. If the third condition is not satisfied, go and check for the fourth condition. Okay. Okay. Now we have to change the output of this one. Inputs also this one. You please change it. And very, very important thing is that you have to write it as a register data type. Huh? It is a register data type. Okay. We stop here today. And this is how we have to write the behavioral modeling. And these are the syntax of how to write the behavioral modeling. Please try to change the sum value and carriage values of this particular, right? We'll see some other remaining concepts and the modelings in the next class. Stop here today.